Okay, let's do a bioenergetics problem. So this will be similar to your problem, I believe 3 on your homework. So in this case, we are talking about acetogenesis. What that means, aceto meaning acetate, and genesis meaning creation. So in this case, we're creating acetate. So certain microorganisms can do this under anaerobic conditions. And what they do is they take CO2 and they convert that into acetate. And they do that using hydrogen as the electron donor. All right, so first we're asked, let's write a balanced equation. So this is a little bit unusual because it's a little bit backwards from what you're used to doing with the oxidation. In this case, we're reducing the CO2 into the acetate, but it still works the same way as far as balancing the equation. So here we have CO2, and we're going to be balancing first the carbon. And in this case, we are balancing the carbon with our acetate. So we have one carbon over here, so we're going to put 1/2 of an acetate over here. And that way our carbons are now balanced. Next step, we're going to be balancing our oxygens using water. So we can do this step right here. And notice that we have 1/2 times 2 oxygens here, so that's 1 oxygen on this side and 2 oxygens on that side. So we need to add 1 water to this side to balance our oxygens. And then next we're going to balance our hydrogens with our protons. So notice we've got some hydrogens over here, none over here, so we need to balance our hydrogens with our protons on the left side. Okay, so we've got our hydrogens balanced now. Now we have to balance our charge. So we've got plus 3.5 over here and minus 0.5 over here. So to balance that, we're going to need to add four electrons to the left-hand side. Okay, so now we have a balanced half reaction for our CO2 reduction to our acetate. Now we're going to do our oxidation reaction, and that's our hydrogen here is going to be converted into, so we can do the same balancing steps here, so we don't have any carbon or nitrogen or other things to balance. And then the next thing is we don't have any oxygens, so we don't need to add any waters, but we do have hydrogens, so we need to add or have 2 hydrogens on that side. And then if we want to balance our charge, because this is 0 charge and this is plus 2, we will add 2 electrons, and that is our half reaction for our hydrogen oxidation. So now we want to make sure that we can get both in the same terms of electrons. So in that case, probably the easiest thing is to multiply this equation by 2. And so then we get 2 hydrogens go to 4 protons plus 4 electrons. And now we have the same number of electrons for this reaction as we do in there. Then we can go ahead and add everything together, and if we do that, we should come up with this equation here after canceling out any terms that cancel. And now we have our final balanced reaction for this acetogenesis process. All right, second part to this is we want to see if we have, for example, for an acetate concentration of 0.1 moles, and we have a pH 7 and a CO2 partial pressure of 0.30 atmospheres. We need to find out what is the minimum H2 partial pressure in atmospheres to make the reaction thermodynamically feasible at 25 degrees Celsius. Okay, so move that over, make sure you can see that. So to kind of talk about this, how we know a reaction is thermodynamically feasible is if it has a delta G that is a negative number, right? And so at that very minimum hydrogen concentration, we can expect the delta G to be going from 0 to a negative number, right? So our very, very minimum to kind of solve for that condition, we want to make sure that we're solving for the condition that our delta G is going to be 0, right? So that's going to be that cutoff line where if you continue to increase the hydrogen partial pressure over here, it's going to make it more thermodynamically favorable. So recall Le Chatelier's principle. If we're increasing concentrations of our reactants over here, it will push the reaction in this direction towards the products. So if we have this minimum hydrogen concentration, if we go above that, then we should be making our delta G go negative and be thermodynamically feasible. So we're going to solve for the condition where delta G is equal to 0. So now we have this equation that we can use. Delta G is equal to our delta G naught. So this is our delta G under standard conditions, but we don't have standard conditions. We have different concentrations of things in our system. So we need to figure out first what this delta G naught is, and then we can figure out what our actual delta G under actual conditions would be. So we have this equation that we can start with, and here we are going to put in our 0 here for our delta G. And then we can rearrange this to say our negative delta G naught is equal to our RT natural log of K. All right, so I'm going to push this up here so we can still see it, and we'll continue on the next sheet. Okay, so let's look at our equation first of all. So we have CO2 plus 2H2 going to 1/2 acetate plus 1/2 proton plus a water. Okay, so we need to get our delta G for this equation, and so to do that, we're going to look up our delta G of formation. And so this is under standard conditions, the delta G of formation. And so for CO2, we find that's negative 394.4. For hydrogen, we'll have 2 of those, but for hydrogen, it is 0 for our Gibbs free energy of formation. Actually, let's move this a little bit over here so you can see everything I'm writing. And then over here, we have 1/2 acetate. Acetate's Gibbs free energy of formation is negative 299.78. We have 1/2 of a proton, but a proton has a 0 Gibbs free energy of formation. And then we have 1 water, and that is negative 237.17. And so now we're ready to go ahead and calculate our delta G naught, which is equal to this quantity from the left side all added up minus this quantity from, or I guess I said that incorrectly, this quantity from the right side all added up minus this quantity from the left side added up. So here we have 1/2 times negative 299.78 plus negative 237.17, all of that minus our negative 394.4. And I just left out the ones that are zeros. And then we calculate this, and we should get 7.34 kilojoules per mole. So if we were to look at this under standard conditions, this would not be thermodynamically feasible because we have a positive number here. But we're not under standard conditions, so we have to take that into account. And the way we're going to do that is by coming back to this equation first. And so we're going to go ahead and solve for our K first. So we're going to put that into this equation. So we have negative 7.34 kilojoules per mole. And I'm going to convert that into joules, and you'll see in a minute why. And that is equal to our R value. In this case, I'm using the most convenient R value, that is 8.314 joules per mole per Kelvin. And so this is why we're converting from our kilojoules to our joules, so that we can use this, this R value right here. And we're under 25 degrees Celsius, so that corresponds to 298.15 Kelvin. And then we have times our natural log of K. All right, so then if we go ahead and rearrange and solve for K, we should get 0.051763. All right, now we have our K value. So then let's look at our actual conditions. So our actual conditions mean that our K should be equal to let's start with our H2O on our left side, and there's only 1, so that's to the 1 power. Then we have a proton, and we have 1/2, so that's to the 1/2 power. And then we've got an acetate, so times our acetate concentration, that is also to the 1/2 power. All of this divided by our CO2, which we have on the left, and our hydrogen, which is to the 2nd power because we have 2 of those. Now, one thing we do know is that water is a liquid, so this is equal to 1, so we can sort of ignore that, if you will. Now, our proton concentration, we're given the pH, so our pH is 7 in this case. And so if we convert that to our proton concentration, that means that will be 10 to the negative 7th moles. So in that case, we have that. We have this concentration, which is given, and we have that partial pressure, which is given. So now let's go ahead and fill out our full expression here. So our K value is equal to 10 to the negative 7th to the 1/2 power times 0.1 to the 1/2 power divided by 0.30, that's our partial pressure of CO2, times our hydrogen concentration squared. And so then you can rearrange that, do the math, and you should get a hydrogen concentration of 0.08 atmospheres. So that corresponds to about an 8% hydrogen concentration if you were at a atmospheric pressure, which is very, very, very high. And so that's why acetogenesis requires very specific conditions. So you would need at least, so this is our minimum hydrogen concentration in order to make that reaction actually go in the direction that it's written.